First thing to just mention is that the next homework that would normally be handed out right now, I have half of it typed up, but because of the snow day, I wasn't in the office yesterday, so the second half will be typed up right after class and posted on the web. If you want the first half, if you're really finished and want to do something, I have copies first half. Well, basically what it amounts to, it is going to be, there's a problem where you just write out matrix elements. You just take this Lagrangian, write the matrix element, take that Lagrangian, write the matrix element. And the second part is to put those into Feynman diagrams, because we're going to give you the rules for Feynman diagrams today. Take this process, write a Feynman diagram, take that process, write a Feynman diagram. Okay? There are things that, if you know what you're doing, you can do in, just as fast as your pen goes. If you don't know what you're doing, you get there. Okay? Who knows how long it takes. You come talk to me. Okay, so that's the next step. But today we have to do the Feynman rules. So actually, I haven't derived everything, but let me give you the Feynman rules for one theory right now, because we then go through the example and you get to see all the pieces emerge. Okay, so I'm going to give you the Feynman rules for lambda phi to the fourth theory. The Lagrangian is minus lambda over 4 phi to the fourth. So it's a scalar theory. We've done one example with that. Okay, and these rules are rules for the matrix element, which we've been calling script M. So in general, if I have a process, any old process, there's 2 pi to the fourth delta 4 of p initial minus p final. So the overall momentum conservation, there's a bunch of normalization factors, 2 omega 1 for every external state, and there's something that we call minus Im. Okay, that's the amplitude that will go into things like cross sections and decay rates. Okay, and these are the rules for minus Im. Okay, minus Im will be given by these rules. Okay, so the rules start off, you draw all possible connected diagrams. Okay, and the assumption is that this is to some order in lambda. You typically always work to the same order in lambda. Okay, so one of the words in here has to be explained here. We have to do connected. What does connected mean? Okay, draw all possible diagrams. I think you understand. Okay, we will reserve to later self-energy diagrams. Okay, so I have to explain what that is also today. So that's part of the game plan for the day. Then in each of these, for any diagram then, minus Im equals something. Okay, and so we have a bunch of rules that come from that. You put, and these rules have the following features. There's, at each vertex, there's a factor of, it's plus I Hamiltonian matrix element, or, no, plus, I'm sorry, it's minus I Hamiltonian, or plus Lagrangian matrix element, which that phrasing is general. Here, this is minus I times lambda over 4 times 4 factorial was the counting factor is minus 6I lambda. Okay, so at each vertex you get that. Now we got that factor once already. When we just did the simplest lowest order diagram, we got minus 6I lambda for minus IM. So that's typical thing you get. It should be said that here that you're dropping any 1 over square root of 2 omegas and e to the I p dot x's. So those guys have disappeared because they go into that external factor. Okay, but whatever's left over, you just take the matrix element of a Hamiltonian or Lagrangian. And of course the reason why this happens is because the time development operator has minus I Hamiltonian in it. And so that's always happens. Okay? The next thing you do is there's momentum conservation at each vertex. We've already seen that once. We'll see it again today in our calculation. For any internal line, you put a factor of the propagator, I over q squared minus m squared. Okay? Where q is determined by what the momentum conservation is. Okay? Then here's another new guy for us. If any momentum is not fixed, if it's not fixed by momentum conservation, then you integrate over it. You then have d4q over 2 pi to the 4th. Okay, this is going to be the momentum that flows in loops. We'll see that it's not fixed. So this is also part of today's lesson. And the lesson's a bit of a fussy one. If you have 2 bosons of the same type, in a loop, there's a fussy factor of a 1/2. Okay, so 2 bosons of the same type. Okay. Now let me show you an example where this rule comes into play. It's a diagram we're going to calculate, and so P1, P2, P3, P4. Now let's make them P's. Okay. This is one of the types of diagrams that in the intermediate state here, there's 2 scalars of the same type. You put a factor of a 1/2. So there's a... Okay. And let me give you the reason. It's not completely obvious. But remember, we're supposed to, the rule right above it says we integrate over all possible momentum here. And there's then a double counting that happens when you do this. I always find it easiest just to make specific momentum here so that you can see this. So let's just put the momentum labels there. Let's imagine that this guy was 10 and this guy was 7. Okay? That's the incoming momentum, so I'm giving you numbers there. Well, there could in the intermediate state be a case where this guy is 12 and this guy is 5. That conserves momentum. And there's another case in it where this guy here is 5 and that guy here is 12. Okay? And our instructions are to integrate over all momentum. So in fact, you find both of those cases there. You know, all possible momentum gets found because of that loop integral. But these are actually the same state. This is two bosons, one with momentum 12, one with momentum 5. So they're identical particles. So if they're two bosons of exactly the same type, those are both the same state. And the 1/2 removes the double counting. Okay. In practice, you don't have to have those thoughts beforehand. You'll see. We're going to do the calculation. The answer is just going to fall out right then and there in the calculation. And so if you're ever in doubt, you just go back and redo the calculation like I'm about to do, and you'll find it. But that's the physics of what's going on. That's why it occurs. If this was a fermion and an antifermion, for example, we'll see loop diagrams with a fermion antifermion pair there. You don't find that factor, neither when you do the calculation out in gory detail, nor should you see it in this case, because in these cases, that a fermion and antifermion needs to be two different states. One case the fermion carries 12, in the other case it carries 5. So those are two distinct states. But if they're the same bosons, they're identical particles, it's the same state. Okay. So we'll see that. Okay. So that's what the Feynman rules look like for this theory. You have a matrix element, you draw all these diagrams. The self-energies we're going to deal with when we deal with renormalization, but all the rest we write up. So let's go. We're going to find these. Okay, what I'm going to do is I'm going to do, as my example, lambda phi to the 4th 2 order lambda squared. So next order. Okay. So remember, at first order we did it. It was at first order, at order lambda, we had just this diagram, minus im is minus 6i lambda. That's Fineman rules, and our calculation gave that. But now we have to get to the next order. Okay. So let's start off. Some of this is painful, but okay. So the time development operator, the S matrix, or the time development operator from minus infinity to plus infinity, is, when you expand it, is 1 minus I lambda over 4 integral d for x phi to the 4th, and then the next term is minus 1/2 time ordered product integral d for x d for y lambda over 4 phi to the 4th at x lambda over 4 phi to the 4th at y. Okay, so that's what has to be time ordered. So at second order, then at order lambda squared, so then plus dot dot dot, order lambda squared, we're interested in taking matrix elements of, so it's TFI is P3, P4, so this is at order 2, P3, P4, minus 1/2 integral d for x, d for y, lambda over 4, phi to the 4th of x, phi to the 4th of y. Time ordered block P1, Okay, there's our big guy. Okay, and so if you stare at that, you see it's pretty easy to make the transition. There's lots of things here that can annihilate these states and others that create those states. But there's more than enough. Okay. There's 8 field operators here, and there's 4 external states. And so there's too many field operators. They can't all act on the external states. Okay, and that's where Mr. Wick comes in. Wick's theorem. And we talked about last time says that anything, any phi's that don't act on an external state end up in time-ordered products of propagators. Things like that. Okay? So, you know, more precisely, Wick told us that if I have time-ordered, let me just write it as phi to the 8th, just because I'm doing shorthand. There'll be lots of terms in this thing, but one of them is normal-ordered, phi, 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 and then 0 time-ordered phi, phi. No. Sure. Close and reopen it. All right. Come on. There we go, good. All right. Okay, so there will be things with propagators in it where these guys act on external states, these guys get contracted, and they turn into propagators. Okay, so that's basically what we'll do. Anything that doesn't act on the external state turns into a propagator. And our rule is just drawing pictures and sticking in propagators. People happy enough with that? Questions are welcome. Okay, so let's draw some pictures. Okay, well, the one type of thing is we have these 2 different points here. So you can take one from one point and annihilate both of these guys, take 2 from that point, create those guys, and have the internal stuff be propagators. Okay, so you can, that type of diagram will look like the one I drew there before. Incoming guys hit at one point, there's 2 propagators go to the next point, and then things come out. Okay, so one of these is X, one of them, let's pretend that's X and that's Y. So that could happen. Okay, there's a bunch of other things that can happen. So go back up here. One of these could annihilate from the initial state, and another one could do a final state, and likewise over here, one from this guy, one from that guy. Okay, So there's some diagrams that look like one initial, one final, propagators, one initial, one final, where this is x, that's y. Okay. Okay, well, there's going to be another one where it goes like this. I'm sorry. So if this is 3 and this is 4, this is 3 and this is 4, they come out. So it's just a question of which one gets annihilated. We can talk about that one later if you want. That's just the general classification. Okay. Well, there are other things that can happen too. I could take 2 of these, annihilate both of those, take another one, create that final one, and then there's only one left to act. So from this guy I take 1, and then I can track the things up all possible ways. Let's draw the picture and you can sort of see it. This one is, so I've taken those from one point, and I've used 3 from the point x to annihilate the 2 initial ones, create a final one. From the point y is sitting over here, it creates one of the final ones. And then there's some propagators. Well, the only way you can actually do it is you go like that, okay? One of the x's, if you come back up here, you can see you had one x left, or one y left over, or one x left over, and 3 of these guys. So 2 of them get contracted with themselves. That's where the propagator comes out, ends at the same point. They start and ends at the same point, and 1 goes from x to y. You got to get rid of that last guy. Okay, so there's a bunch of diagrams that look like that. Let's draw another one like that, plus dot, dot, dot. This is the class that I call self-energy. Okay, because this little box there is going to be what we'll describe later as a self-energy. Okay, so you can break it up that way. It's not to say that these things don't exist. They do exist. And they're for real. There's physics in them, but we're postponing them. So I've just postponed them because I haven't told you how to deal with them yet. Okay. Then the other things that you could do, if you go back up here again, our master formula, you could take all 4 of them from one of these 2 guys. So here, all 4 of these guys take this one, create that one, and so everything happens with phi to the 4th, and this guy, there's 2 propagators left over, but they both start at x and end at x. So they come around, they start and end at the point x. Okay, so Mr. Wick would tell us that we have propagators, but both their labels is x to x. Okay, so this would be a diagram that looks like this. There's the point x, here's the point y out here, and those propagators start and stop at the point y, x, y. Okay, and there's a bunch of those too. Actually, there's 2 of those. This is x and y. Okay, this is what's called the disconnected. There's no connection between the 2 points, and one of my tasks today is to explain why you drop these. Okay, so there's the classification. These are the good guys. Those are the most important dynamical ones. Self-energies are interesting and will be dealt with later. So to be honest, I can give you the punchline. These go into the renormalization, the change in the mass of the external state. These just, if you think of this as just looking like a propagator out here, this looks like it changes a propagator on the external line. That's what self-energies do. And it's a little work to show you how we deal with them, but we'll deal with them separately. These guys are important. These are less so, and these drop. Yes?
The first one, the second one is self-energy.
That's the self-energy also. So these are basically renormalizing the properties of the external line. That's what they do. Okay. But I don't show you them for a while. All right, so I think we've got all our pictures out there. So let's calculate one of these. Well, I'll take this guy right there and calculate that. Okay. So we've done a bunch of these, but there's certainly a big counting factor issue here. So we have minus lambda over 4 squared. There's a minus a half lambda over 4 squared from the fact that we're second order. There's the minus a half lambda over 4 from that. We have P1, P2, time ordered product, phi to the 4th at x, phi to the 4th at y. P1, P2, and I wrote this wrong. It's P3, P4 in the final state. Okay. So that's what we got to do. So we're doing, just to remind you, we're doing this diagram here. P1, P2, P3, P4. Okay. So here's our counting factors. Okay. So there's two ways to start off. Remember, I'm taking some point, one of these, and annihilating P1, P2, P3, P4. I could take X or Y to start with. So there's two ways to start acting on the initial state. So that's X or Y. So I'll choose one, I'll choose X. X goes there. Okay? Okay, so that leaves Y to be the second vertex. X on the final state. Now, I have to annihilate the P1. So I'm taking X, phi to the X, and using an annihilation operator to act on P to the 1, P1. There's 4 ways to choose that. Okay, so out of phi to the 4th of X. Okay, so we've got 4 of them there, so I take one of them, I annihilate it. There's then 3 ways to do P2, to annihilate P2 from that guy. And while I'm at it, let's do the counting factors in the final state the same way. There's 4 ways to create P3, and 3 then ways to create. Okay. So now I'm left over with, so at this stage I'm left with 0, time ordered phi squared at x, phi squared at y. Those are left over. Okay. And there's, now, and actually it's easiest to make this argument if I actually write them all out. So phi of x, phi at y. I've got 2 at x and 2 at y. There's then 2 ways to let these work. Okay, I can take the first of these, connect to the first of those. That requires then the second ones to be connected. Or I could connect the second of these to the first. That requires the first to happen. So if I work out the possible pairings, there's one pairing that goes like that, like that, and there's another pairing that goes like that, like that. There's only 2 possible pairings. You can't find any more out of there. So this turns into a factor of 2 times the time-ordered product of phi of x, phi at x, phi at y, times the same thing again. Okay. All right, so there's my counting factors. And so let's write out the matrix element. Okay. So this transition matrix element, T, is, well, there's an integral d4x, d4y. There's a minus a half lambda over 4 squared. Then there are all these counting factors, which if you look at it, it's 4 times 3 times 2 times 4 times 3 times 2. There's a 2 up at the top, 2 at the bottom, so 4 times 3 times 2 squared. It's 4 factorial squared. And then you get the effects of doing these annihilations. So I end up with e to the minus I p1 plus p2 dot x over the square root of 2 omega 1, 2 omega 2. Remember, that's what we've done for taking that matrix element. For the final state, there's an e to the plus I p3 plus p4 dot y over 2 omega 3, 2 omega 4 root. And then there are these 2 propagators here, which I'll write separately. There's integral d4q over 2 pi to the 4th, I over q squared minus m squared plus I epsilon, e to the minus I q dot x minus y. And there's another one that's exactly the same, except I just renamed the integration variable. d4q prime, 2 pi to the 4th, I over q prime squared minus m squared plus I epsilon, e to the minus I q prime dot x minus y. Okay. All right, so there's what it is. So we're at the most painful moment now. Now it starts getting simpler. Okay, so see all that pain up there? Let's do it. At this stage, we do the x integration. We get a delta function of p1 plus p2 plus q prime. Okay, so q plus q prime is minus p1 plus p2. We get another delta function of P3 plus P4 is Q plus Q prime from the other one. Yes?
Do they have a factorial for the property?
Well, I put that in out here. So there's, let's just go back, show you the counting factors again. We had 4 times 3 from here, 4 times 3 from here. There was a 2 from there and a 2 from there. Okay, so it looks like they're distinct places of 2's, but they're not really. Okay. Okay, good. So if I turn this around, let's make it d4 q over 2 pi to the 4th d4 q prime over 2 pi to the 4th. There's 2 pi to the 4th delta of p1 plus p2. Yeah, I can make my life easier if you let me just change the signs on those. Remember, it's integrated over, so and everything else is symmetric. So I'm going to do that. It becomes minus q plus q minus q prime there. And another 2 pi to the 4th delta 4 p3 plus p4 minus q prime. And then we have minus 1/2 times 6 lambda squared I over q squared minus m squared I over q prime squared minus m squared. Okay, so we're reducing it now. And all those square roots are 2 omegas. Okay? Well, okay, now what you see is obvious. You can do the q prime integration. We've got momentum conservation at each vertex. Q prime integration can be done. That just tells us, that gives us overall momentum conservation. P1 plus P2 equals P3 plus P4 with one factor of 2 pi to the 4th and all these factors out here. So there's then, it's 2 pi to the 4th delta for P1 plus P2 minus P3. It's our last time of writing this out. Square root of 2 omega 1s, 2 omega 4s, and minus im sits here by definition. So we've got the general form. Minus im has equaled. Well, there's a 1/2 times 6i minus 6i lambda squared. There's a residual loop momentum d4q over 2 pi to the 4th because it's still left over. There's an I over q squared minus m squared and another I, but now q prime is gone and been replaced by p1 plus p2 minus q. Okay, so there we are. We're done. Okay, and this has all the features of the rules in it. There's a minus 6i lambda at each vertex. There's a propagator for each of those internal lines. Momentum was conserved at the vertices. Maybe I should draw that out just to show you how that works. We have these vertices that go like that. Here's P1, P2, Q, and this line would be then P1 plus P2 minus Q, so that the vertices are momentum is conserved, and then P3, P4, you bring these together here, they equal P1 plus P2, which by the overall conservation is P3 plus P4. Okay, so we've got momentum conservation. This is the factor of 1/2 from the Fineman rules, that because these two are identical, you end up with that factor of 1/2. Perhaps it's not as obvious why you wouldn't have had that factor of 1/2 if they were different, but that's what happens. Okay, and so here's our number. Just for future reference, I'm going to call this I. It's a function of P1 plus P2. So it's just a function of those momentum only after you do the integration. And we have a task ahead of us of telling you how you do this integral. That's not the easiest of integrals to do, of course. You have to integrate over all possible for momentum, and you've got poles sitting around there. Suffice it to say, we're going to use complex variable techniques. These I epsilons are important. Let's write that last one in there and be a little fussy. I epsilon. Those I epsilons are important in telling you how to do that. But there's the answer. Okay. So just a couple other diagrams we can see. If I did this diagram here, P1, P2, 3, P4, then minus IM is, there's a 1/2 from the Feynman rule, minus 6I lambda squared times the same function. It's the integral d4q, just like above, propagators. The only difference is that you end up with P1 minus P3. It's the same integral, but it's a function of P1 minus P3. Okay, and let's see how you can see that. If I take this in there and I put this guy as Q, then the momentum flows here would be P1 minus P3 plus Q. If I draw the arrow down, it's minus that if I draw it up. So the factor that sits in the other propagator is Q minus P1 minus P3. Okay, so it's a function of P1 minus P3. It's the same function. And the other interesting diagram is the one where you do, I keep in trouble there. Okay. When I draw that little arc around, it means it's not a vertex there. Okay, so this, if I label this thing P1, P2, P3, P4. What this means here is, if I drew it through, you might think there's a vertex there. This means that this passes by that line without interacting. Okay, and this, in this case, minus IM is 1/2 6I lambda I. Well, it's a P1 minus P4. It's the same sort of deal. You label the momentum, you see that if this is Q, this is Q plus P1 minus P4. Okay. So those are the functions. And in the end, John.
How are those two diagrams significantly different? It just looks like the...
Yeah, I've just changed.
Crossed them over and
Yeah,
changed,
you in fact used the right word. I've crossed the final states. Right. So they're different as numerically because this is a function of P1 minus P3. This is a function of P1 minus P4. So they're and in the counting, when you're trying to write out all these possible vertices, if this one was X, it acted on P1 and P3, and this X acted on P1 and P4. It's just, it's just another term that happens in the rule, draw all possible diagrams. Okay?
Is there a square in that?
There's a square in that last term, thank you. Yes. Right there. Yes, good, thanks. Okay. So aside from the self-energy diagrams, the two-order lambda squared, the answer is the matrix element for the scattering is minus 6i lambda plus 1/2 minus 6i lambda squared I of P1 plus P2 plus I of P3, I'm sorry, P1 minus P3 plus I of P1 minus P4. Okay? And that's the relevant amplitude for the scattering. And it just summarizes the lowest order picture plus the ones that we did above. Okay. All right. So our future tasks involve evaluating that, but that's to come. Okay. So if I go back up, I think I've explained almost all the Feynman rules here. There we go. We drew all diagrams. We reserved till later self-energies. We have those vertices, momentum. We explained the bosons of the same type. We explained the angular momentum, the loop integral. The thing we didn't do is this guy here. We didn't explain why you dropped the disconnected ones. Okay, so the last thing to do to complete our construction of the Fineman rules is disconnected diagrams. Okay. Okay, the disconnected diagrams again were ones that look like that at one point and there at the other point. And the logic, I'm not going to do all the steps, but the logic is that this amounts to just a phase correction for the lowest order diagram. And I think the easiest way that I know to make that case is let's look at the following. Let's look at the amplitude to stay in the ground state. Okay, so that's ones where we start off like with nothing. We develop it infinity to minus infinity with the time development operator, and we end up with nothing. Okay, that's what we expect should happen. If you start off with nothing, you're not going to produce anything, and things don't just spontaneously appear. At least in this setting. So you expect that that should at most be a phase. It could, it could be a complex number, but its amplitude should be 1 because okay, and the diagrams for that are 1 plus this phase this vacuum guy. So, there's no times where things act on the external state, so you would have written that. At next order, you would get diagrams like this. You also get some other fancy bubbles that look like this. Plus dot dot dot. So you keep going. Okay. So the sum of these is at most a phase. E to the I theta. Okay. And in fact, it's actually not that hard to show that these guys exponentiate and are a phase. It's just a bunch of counting factors. Every time you see the Hamiltonian, you draw these bubbles. And we start off with e to the I Hamiltonian, and these things exponentiate back up into a phase. Okay. And so the point is that this phase occurs both in the numerator of any scattering process and the denominator. So we might have a better definition of the scattering amplitude. Okay. So I might have T Fi is the what I want U of infinity minus infinity initial, and let's divide out a phase, just the vacuum phase. Okay, and so doing this pictorially, we would find that for our scattering amplitude we have this picture there, 1 plus that picture plus if we went to yet next order, it would be that picture plus this picture plus that. That's all these disconnected diagrams divided by 1 plus that. Okay. Basically, the point is that these disconnected diagrams, you either say they sum to a phase or they're canceled by this vacuum transition amplitude. And so all these disconnected diagrams are common. They're a common phase. They don't change any transition amplitudes, so you drop. Okay. So that's the logic there. Okay, comfortable with that? Questions? If you are, then that's the Feynman rules for lambda phi to the fourth. And let me just give you Feynman rules for all the rest. You can sort of see how they occur. They're all the same. Well, the other example we did, the interaction Lagrangian was minus, I think I used minus Q, chi dagger, chi, phi. Okay, this was our toy model for QED. And the only change in the Feynman rules is there's a vertex. The vertex has a chi, and the phi associated with it. And that's given by, you take minus I interaction Hamiltonian or plus I interaction Lagrangian, and you drop the 1 over square root 2 omegas, etc. That's always going to be our rule. And so you end up with minus IG is that vertex. And that's what we saw when we did. So everything else is the same. Okay, there's no change in it. Okay, so let's just remind you what we did before we did the chi. So it was chi E, chi P, chi P. This is minus I M was minus I Q E, I over Q squared minus M squared plus I epsilon minus I QP. Okay, so that's just the same old rules. And Q was determined by momentum conservation of the P1, P3. Then Q was P1 minus P3. So Q squared was that. Okay. Okay, so everything else is the same. Okay, let's do another one. Scalar QED. So now this is the real QED, but with a complex scalar. So the Lagrangian interaction Lagrangian. So remember, the original Lagrangian starts off. The original, the whole guy is minus a quarter F mu nu, F mu nu. That's an F. Plus d mu phi star d mu phi. In fact, that's all we need for scalar QED by itself. So the interaction pieces are the pieces that involve the A's there and the derivatives. It was minus A mu times there's a Q, whatever the charge is, phi star I d mu left minus right, phi. Plus there's also a piece which we hadn't talked about much before, which is the A mu phi star phi. Okay. Do I need to say any more than that about what these terms are? They're sitting here. Remember, d is the usual derivative with an I minus IQ A mu. And so the A piece is, linear A comes with one A and one derivative. That's that. Or there's two A's, an A from there and an A from there, which is just AA phi. Okay, so here, most of the rules are the same. We have vertices. If I have something that looks like that, P1, P2, Q, well, let's call it K. I don't know, because my trouble is I've got Q as the charge here. Is minus I charge P1 plus P2 mu. Okay. Okay. So that's there. If I have a vertex that looks like this, P1, P2, there's also a vertex with photons, K1, K2. That actually comes from this interaction right here. You just take again, it's minus I times the Hamiltonian. This turns into 2I charge squared. So this is okay, charge, not momentum transfer, times g mu nu. Okay, the 2 came from there's 2 A's here. There's a counting factor of which one is mu and which one is nu. The fact that they're connected up here in the Lagrangian turns into g mu nu. Okay. There's propagators. The scalars are unchanged, but for the photon, you use minus I g mu nu over q squared plus I epsilon. Okay, so here's this propagator. We label one end by mu, the other end by nu, and its momentum here is q, and this is momentum transfer, not charge, so maybe it'd be best to call it k squared and call that k squared. Okay. So anytime you have a photon propagator, you stick that in there. Notice that there's a minus sign there. That's just, it's how it works out. The other change is that there's a new rule, external photons. You add epsilon mu or epsilon star mu in the initial state or final state. Okay, I guess I have some time to do an example. Let's do an example. Okay, this example is what would be called Compton scattering. Okay, which is a photon on a particle. So I'll call it an electron, goes to a photon plus a particle. So light scatters. Okay? So let's draw the diagrams here. Okay, so let's work out the diagrams. You can have the photon coming in, hits the particle. There's a direct vertex that goes like that. Right? So here's, I'll use P. P1, P2, P3, P4. Okay? That's a possible way to get from that initial state to that final state. And the rule is, and so this guy carries momentum P1, index P2. This is nu, so this is 2I, thanks, times the charge on the electron squared, times epsilon mu for the initial state of, so P, a function of P1, epsilon star mu P2. Okay, so that's that matrix element. Okay, there's actually two more that we have to do. Let me do them also. At the same order in the charge, I have P1, P2, P3, P4. Okay, here the answer is then I have minus IQ. All right, let's label this guy. This is P1 plus P2. Is, I can call that K. The vertex, the rules tell us that if I have two momentum there, I do use the sum of the momentum. So it's P1 plus P1 plus P2 mu. I have a scalar propagator I over P1 plus P2 squared minus m squared minus IQ. At this vertex, it's P4 plus, I should tell you that this is P1 plus P2 is also P3 plus P4. P3 plus P4. This guy's nu. And then I end up with epsilon nu mu epsilon nu star, just like before. Okay, are we comfortable with that? So vertex, propagator vertex, this guy turns into 2p1 plus p2. This guy turns into 2p3 plus 2p4 plus p3. And I've got this one backwards also. P3. But aside from that, that's the amplitude. All right, I got one more to draw. One more to draw is this guy. This is one where people would often miss this first time through. So here it is. Those don't interact, they just pass through each other. So P1, P3, P2, P4. This is also a possible diagram. You emit at this vertex, the final one. You absorb the initial one at the second vertex. So it's also one of the possible permutations of this. We'd write this out as label that intermediate state. That's P2 minus P3, which is also equal to P4 minus P1, because momentum is conserved at both those vertices. And this amplitude, let's just write it out quickly. It's minus IQ. It's 2P2 minus P3 mu I over P2 minus P3 squared minus m squared minus IQ. It's 2p4 minus p1 at this vertex nu with external epsilon mu's, epsilon star nu's. Okay, so those three amplitudes are the tree amplitudes for Compton scattering in this theory. Okay, I have one last thing to do. Let's do real QED. Let's do fermions in QED. Okay. Okay. So there's, for fermions, there's in T, there's no factor of 1 over square root of 2 omega. Okay, so this is just a consequence of our normalization convention here. Okay. The other things you get are, for external fermions, you get U of P for incoming fermion, U bar of P is outgoing fermion, but these are only externals. V of P is an outgoing antifermion, and U V bar of P is an incoming antifermion. Remember, those are backwards. We had those rules before. With fermions, anytime you have a propagator, you use I over the momentum minus M plus I epsilon, I over P slash minus M. So you use the propagator for fermions, which we derived. Okay. There's an oddball rule. It's like that a half rule. So this guy is unusual. This is -1 for closed fermion loop. Okay, so let's imagine here's a closed fermion loop, something like that. You put a loop there, and this comes from the anti-commutation rules. If you just sort of you write this thing out like we did before, and you just look at all the permutations, whenever you have a closed fermion loop, there's always a minus sign. It comes from anti-commuting. Okay, and then there's the rule that's specific to QED. Those are all general fermion rules. You have this diagram here is minus I Q gamma mu. Okay. This is just the general rule Vertex is minus I interaction Hamiltonian is plus I in interaction Lagrangian matrix elements, with where you drop the external stuff. Okay, so we've dropped the external epsilon for the photons. We've dropped the U's and U bars. Okay, that's all there is to Fineman rules. That's it. That's them. Really, we need a little practice at them. But we're now going to assume that we can always get these Fineman rules. And your pathway is always this. You look at the Lagrangian plus I, L. What does that give? That's your Fineman rule. Okay, very good. Thank you. Yeah, so I explained there that I haven't, because of the snow day, I didn't get the second part typed up. There's a second problem, which I'll post or bring on Tuesday or. Okay. And these are just simple. If you can write these things out real quick if you understand everything. If not, you'll find out.